We are in lesson 2.6, rational functions. Students are working on these warm-up problems, finding the domain for these three guys, and then seeing if they remember. You don't need points or anything, just a quick sketch of this parent function. I'm going to give them a few more minutes. Seeing some good things. We know with rational, meaning fraction functions, our denominator cannot be 0. So I just have to disclude -5 from my domain, the first one. You can say that, but we've been practicing interval notation for a domain. That is how we would write everything except -5. Technically, this isn't wrong. This is just a better way to write it. Okay, we had two cases in which my denominator was 0. In number 2, x cannot be positive or -2. I don't have any radicals or anything, so I don't have to worry about where it's like positive, just where my denominator is 0 for these three. All right, so I just have to add in an extra interval to say everything from -infinity to -2, and then everything from -2 to 2, and then everything from 2 to infinity. And we can use those unions. Which x value do I need to disclude in number 3? 0. Yep. All right. Make sure you have parentheses around all those values, because obviously we can't include them in our domain, and with infinity, we always use parentheses with the interval notation. Look at this cute little graph in your notes. This little tiny. Just a little screenshot. Anyone remember what this looks like? You show with your arms?
Asymptotes.
Asymptotes, that's a great keyword for today. Looks like up here in quadrant 1. 2 symmetrical branches down there in quadrant 3. That's our parent function for rational functions, one over x. You don't need any points or anything like that, just a quick sketch. If you look at the very bottom of your notes, I give you a little hint with that little picture. Okay, so all about graphing rational functions today and probably a little bit tomorrow. So rational function is anytime we have a quotient of 2 polynomial functions. So your numerator, they call n of x, denominator, d of x when they're polynomials. Obviously, denominator can't be 0. Okay? When we're asked to find our domain of these, which we just practiced, it's everything except when the denominator is 0. So just keep that in mind. Here's our parent function, our most basic rational function, where I have 1 divided by x. You can see my 2 symmetrical branches. And you can also see I have 2 types of asymptotes here. I have a vertical asymptote at x equals 0. So it gets very, very close to, but it never touches vertical asymptotes. And I have a y equals 0 horizontal asymptote here. And this is a value that basically like the ends of my graph kind of approach. I don't know if you knew this, but you can actually cross horizontal asymptotes. Vertical ones you can't. Horizontal ones can sometimes be crossed. Okay, so really the most important characteristic of rational functions are these asymptotes, and it kind of guides us for how we graph these. So let's take a look at vertical and horizontal asymptotes. I often abbreviate vertical asymptote as VA, horizontal asymptote as HA. So if you see that notation, that's what I'm talking about. Okay, I'm going to add in a little notation for these asymptotes that's similar to what you'll see in calculus. And you know what a vertical and horizontal asymptote is. And here's just a little like calculus way of approaching it. If I have a vertical line that's an asymptote, and I gave you this little like example picture. So obviously vertical lines going this way. I have one here at -5 and at 1. What's happening is as our x values are approaching those asymptotes, so that little arrow in math we read as approaching. So as our x values are approaching whatever that horizontal asymptote is, I'm just using A because they said x equals A is a vertical asymptote. When, as we're getting closer and closer and closer to those values from the left or the right, our graph is doing one of two things. All right, now let's look at this. So if I kind of like take my fingers from the left and from the right and go in towards, I'm just going to do -5 first, from the left and from the right. What is my graph doing? Well, from the left, this end is going where? Up to positive infinity, right? From the left. If I look as I get closer and closer, like if I did even like -6, -5.5, -5.1, as I'm getting closer and closer to 5, my graph's going off to infinity. Or something else that could happen, let's look at what is happening if I'm coming into x from the right-hand side. So if I'm looking at x values that get closer and closer and closer, this graph is going down towards -infinity. So that's kind of what the behavior of my graph is doing around vertical asymptotes. Either they're going to approach infinity, or they're going to approach -infinity. If that characteristic happens, then we have a vertical asymptote. Vertical asymptotes can't be crossed or touched. And I think I put that in our notes later on, but if you want to add it in right now, you can. When we get to graphing, yep, I put graph never touches vertical asymptotes. Okay. Horizontal asymptotes, another kind of way of looking at those, is we're basically looking at like our end behavior of our graph. We're looking as x gets really, really large or goes off to infinity, or -infinity. So now I'm not like zoning in on an x value. I'm kind of looking, like I said, at my end behavior of my graph. So as x approaches infinity, and we did this with end behavior. Remember I was saying that's like the right side here. Is my graph approaching some value? And if we look at this example here, as these x values get larger and larger and larger, you can see it's kind of leveling off there to a y value of 3. So as our function is going off to infinity, if your function levels off to some value, to some b, then there's going to be a horizontal asymptote there. Look here. This is a good example. My graph crossed that horizontal asymptote. That can happen. Now, as x approaches -infinity, we're kind of looking at this end behavior. What does my graph look like? It's kind of leveling off to here. What value? What x value?
3.
3 again. Yep. Now, it doesn't have to be the same in both directions in order for it to be a horizontal asymptote. It could be going off to 3 in this direction, and then be -3. Did I touch the board?
Yeah.
With what finger? I don't feel
I
it.
didn't feel like brush it.
Oh, we had these strings.
Yeah.
I've done that like 16 times already today. Okay. It could be approaching two different things in two different directions. We could have horizontal asymptote at 3, like I said, -3. And then just keep in mind your graphing processes. Okay. Let me ask you guys this question. You've probably graphed these before, yeah?
Yeah.
Okay. Have you ever graphed ones where you have to find the horizontal asymptote and it depends like what the degree of the denominator and numerator is?
Nope.
Okay, cool. You'll like this. It's a nice little pattern that holds with rational functions, and this looks way more wordy than it is. Let's break this down. So if we have a rational function, we have some polynomial over another polynomial, right? We will have a vertical asymptote whenever our denominator is 0. So you just take your denominator, set it equal to 0, solve for x if you need to. That's going to be where your vertical asymptote is, because those are undefined values, right? We can't have our denominator be equal to 0. So our graph, what happens there, the behavior, we can get really, really close to those values, but we can't actually plug them into our function. Hence, they form these asymptotes. Okay. Here are how you can compare the degrees to determine where there's a horizontal asymptote are. Now, when these are polynomials, you can have at most one horizontal asymptote. Figuring this out, and we'll only look at examples that have one horizontal asymptotes, but like I said, there can be more than one. But with polynomials, all you have to look at is the degree of your numerator, so that's what they're calling like n. And your degree of your denominator, that's what they're calling m. Here's the relationship. This is so cool how this works out to me. If your degree in your numerator is less than the degree in your denominator, the graph is always going to have a horizontal asymptote at y equals 0, or the x-axis. Okay, so if this is true, degree in your numerator is less than degree in your denominator, we'll have a horizontal asymptote at y equals 0. If they are the same degree, which I may be guessing these are ones you've done before, we can find the horizontal asymptotes by dividing the leading coefficients. I think that's familiar to you. So here, this is your LC of your numerator. And that's what's the same here. Take your LC divided by your LC of your denominator. And this is like the strategy used to find these. Last case scenario, and we'll look at some examples of this. If the degree in the numerator, and think the notation they use, n, think n numerator. If the degree in the numerator is greater than the degree in the denominator, then there will not be any horizontal asymptotes. And we could have something called a slant asymptote. Is that familiar? Oblique asymptotes.
No.
Cool. Good. Yay. Something new. Okay.
I like the idea.
Let's try some before we throw in the slant asymptotes. Let's practice just finding some vertical and horizontal asymptotes if they exist. I'm going to start with letter A here. Before I start trying to set my denominator equal to 0 or applying any of these like rules for my horizontal asymptotes, I first like to factor it if I can and like simplify my rational function. And when I go to graph it, that's always my first step anyways, is to see if I can like simplify it a little bit more. Okay? So up top, somebody factor that for me.
X minus 3, x plus 2.
No, never mind.
I think you meant x minus. Oh, you were doing the denominator?
Oh, yeah.
Sorry, what did you say? X minus 3?
Yeah, x plus 2.
Okay. So here's my factored form. Now, if I were to simplify this rational fraction, what cancels out here? The x plus 2's end up canceling out. So you're like, I know negative 2 is like not a part of my domain, but since it's no longer in my denominator, is it considered an asymptote? And what ends up happening on your graph, this is important, anytime you have this setup where you have canceled factors, what that means is there's going to be a hole in our graph. Where it's not continuous, when that equals 0. It's not continuous, but there's not an asymptote. Okay, you've probably seen maybe graphs that look kind of something like that. Maybe we need them like piecewise functions too. That's going to happen. It's undefined because it's not a part of our domain. I can't plug in -2 into my function. However, because once I actually simplify this, and I could rewrite this in its simplified form, because it's no longer left in my denominator, it's not an asymptote. All right, so anytime you have cancel factors, that means there's a hole there. I asked my calculus students this year because we talked about this in the first chapter of Calc. I said, do you guys remember that? They're like, we never learned that. I was like, oh, I think it's probably somewhere in pre-calc. And here it is. Should tell them 2.6. All right, so now that it's simplified, I'll start with my vertical asymptotes. Those are the easiest to find. You just take whatever's left in your denominator, figure out when that's equal to 0. So that'd be at x equals 3. Obviously, that's a vertical line, so that makes sense. I have a vertical asymptote. Okay, I'm not asking for my domain or anything like that. Just identifying the asymptotes. 3. Horizontal asymptote. I gotta look. Is my degree in my numerator less than my degree in my denominator? Are they the same? Or is my degree in the numerator greater than? They're the same. So what we do in that case is we divide our leading coefficients. So here my leading coefficient is 1. Here my leading coefficient is 1. So there's a horizontal asymptote at y equals 1 over 1 at y equals 1. When you get to calculus, you will talk about why that works. But that's not for today. Okay, so I ended up having 2 asymptotes and a hole. Very interesting. I want to point out holes don't show up on your graphers. Okay, that's another case where you have to be smarter than your calculator. Holes don't show up. So if I were to graph this one, I'll just do this really quick. X squared plus x minus 2. They will show up in your table, though. X squared, was it minus x minus 6? No idea what my window's at. Okay, so here you can visualize that vertical asymptote at x equals 3. And again, my ends from the left and the right are going down to negative infinity, up towards positive infinity, asymptote. We can also visualize, I can draw in horizontal asymptotes if I want. Does that look like on my end behavior that my graphs are approaching 1? Yep, horizontal asymptote. But they're at -2. It looks like my function's continuous. It doesn't look like there's a hole there. You can even zoom in. Let's get close to that. What's going on over there at -2? Oh, too much. What's going on here? And it still looks continuous. You can even keep zooming in. It still won't show you the hole. Once you go to the table, though, you'll see there's an error. We're undefined there. Okay, there's a hole. Same with 3, but that's for a different case. That's for an asymptote. But just be cautious of that when you go to actually graph these or look at them on your grapher. Graphs don't show holes on the graphs. Okay, let's try another one. You can draw vertical lines on your grapher. You guys probably don't know how to do this. I'll just show you really quick. It's not a tool I use that often. But if you want to better visualize vertical asymptotes, you can hit this draw button, You can draw a vertical line, number 4, and it says, where do you want to go? So I just toggle over here. We're going to get close to 3, and again, their calculator is exact. I could plot that. Yeah, that looks like it could be an asymptote there at x equals 3. Okay, let's try another one. So first step, I want to factor. My denominator I see is factorable. Difference of squares. Nothing cancels here, so no holes. But what's left in my denominator, whenever that is equal to 0, we're going to have vertical asymptote. So I have 2 here. Negative 2 and 2. Okay. Horizontal asymptote. I see my numerator is a degree 1 and my denominator is a degree 2. So when my numerator is less than the degree of my denominator, y equals 0 is going to be a horizontal asymptote. Okay, so just out of curiosity, does this feel familiar?
We found them, but I think we found them a different way.
Okay,
Right there, we might have just looked at the graphs.
got it.
Algebraically.
Algebraically? Okay. I'll be curious when that comes up in algebra 2 to see how that's done. All right. So this is probably new for you. Oblique asymptotes or slant is another word. Yep, this is what we teach in pre-calc too. So we kind of have like this third case scenario that like if the degree of the numerator is exactly 1 more than the degree of the denominator, then we have what's called like an oblique or slant asymptote. So like behaves a lot like the other two where that's just what your function kind of like approaches, and it ends up being like a linear equation because it's like a slanted line like this. So your actual slant asymptotes, I often abbreviate these as SA. They're going to be like a linear function. These mean the same thing, slant and oblique. Your book uses slant more commonly, but oblique is the same thing. And what we'll have to do to find these is we'll have to use division. Okay, and we'll practice a couple of these before we actually get to graphing. Good. And this only happens when the degree of the numerator is exactly 1 more than the degree of the denominator. So you could write this if you want. Okay. This time, they're not asking for vertical asymptotes. They just say find all the horizontal and slant asymptotes of the graph of each rational function. All right, I'll start with horizontal. Degree of my numerator is the same as the degree of my denominator. Love when that happens. All you got to do there is take your leading coefficient. So leading coefficient of your numerator divided by, just like how it's set up in the function, divided by the leading coefficient in your denominator. So y equals 2 is a horizontal asymptote. Slant asymptotes only occur if the degree of my numerator is 1 more than the degree of my denominator. Obviously, that's no, they're the same, so no slant asymptotes there. It's not set up that way for letter A. Okay. Now I see, oh, my degree of my numerator is exactly 1 more than the degree of my denominator. We haven't done this with horizontal asymptotes. I'm going to go back to my cheat sheet quick. If the degree of your numerator is greater than the degree of your denominator, then we're not going to have any horizontal asymptotes. So a conclusion you can make then, would we ever have a horizontal asymptote and a slant asymptote at the same time? No. Because if that degree is greater, that tells us no HA. And if it's greater by exactly 1, then we can find a slant asymptote. Okay, so here's how you find slant asymptotes. This is algebraically, but you probably haven't done this before. So we're going to basically do the division of our rational function. We're going to do 3x to the 4th minus x squared divided by x cubed minus x squared plus 1.
Gosh.
But Can we use synthetic division here to do this division problem? Every fraction is just a division problem, right? So this is really saying this. That's the same thing as this, just written in fraction form. Can we do synthetic division with something like this?
Yeah.
No. Only degree what? 1. Only if it's like x plus something or x minus something. So we're going to have to do, you guessed it, long division. Oh my gosh, they're so excited. The crowd went wild. Okay. So, read this like division problem. You have 3x to the 4th minus x squared being divided by x cubed minus x squared plus 1. So I'm going to go ahead and take that underneath my radical. Now, I like to do placeholders. Helps me keep my work organized. So I even do one for x and for the constant. And I also do placeholders in the divisor. Personal preference. If you don't need them, you don't have to. It just feels easier to me to keep everything nice and lined up. Okay. So this right here will give you your slant asymptote after we're done. So what times x cubed would give me 3x to the 4th? That would be 3x. So we get 3x to the 4th minus 3x cubed plus 0x squared plus 3x. Now the good news is usually it's like 1 or 2 steps you have to do. You don't have to finish the whole problem because you'll see what happens. I'm going to change these plus the opposite. Obviously 0 doesn't matter. Those cancel. I get positive 3x cubed minus x squared minus 3x. Carry down to 0. All right, then what times x cubed would give me 3x cubed? That'd be 3. I'll use a different color. X cubed minus 3x squared plus 0x plus 3. And I'm getting 2x squared minus 3x minus 3. All right, we're actually done because I know we obviously have a remainder here. But there's nothing I can times x cubed by to get x squared unless I did a negative exponent, and we're not going to do that. So once you find your remainder, you're done. And this right here, folks, that's your slant asymptote. And I told you it should be a linear function. So we'd write it y equals 3x plus 3. Let's graph this one so you can kind of see what a slant asymptote looks like. You don't have to do it. You can just watch the smartboard if you want. All right, 3x to the 4th minus x squared divided by x cubed minus x squared plus 1. Oops, I saw that horizontal asymptote in there. We don't need that. What we could graph is our oblique or our slant asymptote here. So slant asymptotes can also be crossed, but you can see how like this end behavior is approaching that slant asymptote. Okay, not a horizontal, not a vertical. It's approaching this y equals 3 line. Again, it can be crossed. Doesn't mean it's doing it in both directions. No horizontal asymptotes here. Looks like we probably have a vertical asymptote if we already set our denominator equal to 0, but we don't have to find that. Okay, that's what they kind of look like. Were there any slant asymptotes on that one picture I gave you? No. Bummer. Do you have a question, or you were saying how cool that was?
No, I was saying how hungry I am.
Okay. Okay. Now that we've kind of like dissected how to find the asymptotes, we're gonna actually sketch the graphs. And whatever we don't get to today, we'll just do tomorrow. The asymptotes are like the very first thing we're gonna find because those will help us basically guide what values we're gonna plug into our table. And we know our functions like approach these asymptotes, so we'll be able to fill in a lot of missing pieces without doing like a whole big long table. Okay. So if you know how to find the asymptotes, you're kind of golden for setting up these problems. So here I just kind of broke it down step by step of what you should be doing. So first, simplify your function if you can, meaning if it can be factored, try to factor it because you might discover something such as a whole. I did not do that for this one just because I wasn't asked to find my vertical asymptotes at all. I was just asked to find horizontal and slant, so I didn't, but you could factor that if you wanted to. The bottom is the difference of squares. I don't know if the top factors. I don't think it does. No, it doesn't. That's what you should do first. Then start by finding your vertical asymptotes, horizontal asymptotes, if there's any, slant asymptotes. Remember, slant and horizontal can cross, vertical cannot. If you're still not sure what your graph looks like, plot some points. I'm always going to do this because those are easy points to find. And then look at some symmetry, especially when we have like those two symmetrical branches, because that'll help you too. And then you kind of just plot your points, connect the dots, approach the asymptotes. They're fun. One other thing, sorry, I want to point out, I just looked at my notes. If the original is not a single function, like as an example, if you have something that looks like this, like 1 minus, meaning it's like not one single term. Part of simplifying that is you do want to rewrite it as 1. Okay, so what I would need to do there is make common denominators, make that x plus 5 over x plus 5. And then I can add my numerators, that becomes x plus 3, keep my denominator the same. That's kind of part of like simplifying. We're not going to do one like that, but if you ever see that come up, begin by making a common denominator, adding it so you can create a single function, and then from there you can easily find your asymptotes and such. For points, I often do to the left and right of my vertical asymptotes. And you'll see me do that, but I think that's all I need to say about that slide. Just drop it.
Yeah.
Even the shoes, man.
My brain is losing power.
Okay. We'll start off with an easy one. First of all, anything I can simplify there? No. All right, so second step. Do I have any vertical asymptotes? Oh, well, when is my denominator equal to 0? 2. I'm going to go ahead and just draw this in as we go. All right. Next, do I have any horizontal asymptotes? That's what I kind of asked myself next. So when the degree of my numerator is less than the degree of my denominator, that's the setup here, because it's a degree 0, it's a degree 1. You guys remember what that means?
Y equals 0.
Y equals 0 is a horizontal asymptote.
I hate when they have like those big black lines and I can't see my graph.
I'm sorry, would you rather take notes in your notebook?
No. I was just complimenting you.
Don't say that. It was PTSD.
We had to do that last year. I almost died.
2, 3 subjects.
What?
You want to do 2, 3 subjects?
Yeah.
Yeah.
For you.
Pretty much.
Builds character.
No focus.
Oh,
Okay, do I have any slant asymptotes? Is my numerator exactly one more than the degree of my denominator?
No.
No slant asymptotes here. And I'm just numbering these the same as like these numbers of like your steps. Simplify, vertical. Okay, so then 5. Last thing I'm gonna do is find the x and y intercepts and then make a table if I need to. And I'm okay with you guys using the tables in your graphing calculator to save time instead of plugging them all in. All right, so x intercepts would be when y is 0. So if I plug 0 in here, I get this. Multiply both sides by x minus 2, I get this. None. No x intercepts.
Yeah.
I didn't even know what you're talking about. Point fingers at me.
I still told you.
Y-intercept, when x is 0. So f of 0 looks like, we get 3 over -2, so -1.5. I don't care if you use decimals. To me, decimals are easier to plot. So that'll be right here. All right, so then the only last thing I would maybe do to make this a little more accurate sketch is to make a table. I'm going to do a horizontal table since I'm running out of room. And just plug in a couple points, and I usually just pick, 2 to the left of your vertical asymptote, 2 to the right. We already plugged in 0. We got out -1.5, so maybe plug in 1. And this is what I'm saying. You can use your table and your graphing calculator for this. While I'm thinking of that, guys, just make sure anytime, and hopefully you've been watching me do this, anytime you type in a rational function, you have to wrap parentheses around your numerator and denominator. Okay, if you do this, like the one we're doing right now, if you do this,
Order of operations.
exactly, order of operations. I'm going to do 3 over x minus 2. So just make sure you're wrapping in parentheses. Okay, I got these numbers for you. This is -3.
Oh, you're so generous.
Yep. I know. And we're thinking this is going to be symmetrical, but just to maybe be sure, let's go ahead and plug in 3 and 4, a couple to the right. And I did get out, 3, 1.5, because that's another kind of characteristic of these. There's a lot of symmetry to them. And that's really enough information because I can connect my dots in a curvy fashion. I know vertical asymptotes, they go up to positive infinity or negative infinity, which that's what it's doing on the left. And then they also approach my horizontal asymptotes as x goes off to infinity and as x goes off to negative infinity.
Yeah, no kidding.
Inequalities are so funny.
Shit. Alright, don't lie. I'll make it.
Okay, let's do one more today, and then we'll call it a day. Deal?
Yeah.
We'll do one more, and we'll save the other 4 on that tomorrow.
Oh my god.
First, can I simplify this?
Yes.
Yes, my denominator is factorable. Let's do it.
So how does that work? I go point in 0 numerator.
Hey, you can't divide by 0.
Yeah, so
Well, you're not left with 0.
He's saying if we did it in the numerator. You can have
0
0.
numerator, 0, right?
Yeah.
0.
Like that's legal.
You can have numerator.
Okay, so these cancel. What does that mean?
Oh, we have a hole.
Good. Yep, let's make that little note. We do have a
You
hole
have a hole line.
at when x is 1. So this is my first step here, simplifying it. So then I'm left with 1 over x plus 5. Make that note to yourself, otherwise I guarantee when you go to graph this, you're going to forget to include the hole. Okay, after I simplify, I look for vertical asymptotes. So when is my denominator equal to 0 with what's left over? -5. All right, this setup with the degrees is the exact same as my last one, where the degree of my denominator is greater than the degree of my numerator, or think that degree of your numerator is less than. So we have a horizontal asymptote at y equals 0 again, and there would be no slant asymptotes. Okay.
So if we have a horizontal asymptote at 0, will there not be any x-intercepts?
Not always, because sometimes it can cross it.
Oh, well, that's kind of dumb.
So you just have to be careful.
Darn it.
Good connection though.
So they can cross the vertical ones, right? But they can't cross the slant and the horizontal.
Correct.
Oh, yeah.
All right, x-intercepts when y is 0. I'm going to use the simplified version here. There's none. So Connor just asked a good question. I don't know if you heard him, but he said, if there's a horizontal asymptote at y equals 0, does that mean we don't have any asymptotes? Not always, because it could indeed cross at some point, so just be careful. Y-intercepts. If I find f of 0, I get 1/5. So it's just cross barely above. All right, let's finish this up with the table quick. Running low on time. I did -7 is -0.5. -6 is -1. -4 is 1. -3 is +0.5. Again, just to the right and to the left of my vertical asymptote. But don't forget, we have a hole at x equals 1. So when I draw this curvy curve, when you get to x equals 1, you need to include a hole. And then keep approaching. Horizontal asymptote as x approaches infinity. Vertical asymptote, my graph approaches positive infinity. This one right here. You just finish our curves. Don't forget about the hole. Be smarter than your calculator.
Yeah.
Okay, we will pick that up tomorrow. Workday Friday.
That's
Ooh,
right.
that's something important.
Oh, who are we recording for?
Bailey's gone.
Oh, yeah.
That's right. I knew that because I